Let's take a quantum system, for example a particle in a box, and replicate it many times. Now let's perform a single measurement on each of these identical systems of observable, say, A. It turns out we cannot predict the outcomes of individual measurements. Using quantum theory, we can only make predictions about the probabilities of various outcomes and about the average result. The average of these measurements is given by the expectation value of the operator associated with the observable that is measured. For an operator A in the wave function psi, the expectation value is bracket A equals, in bracket notation, psi A hat psi, or in integral notation, integral over all space of psi star of x, A hat operating on psi of x, dx. We can distinguish two cases. Case number 1. The wave function is a normalized eigenfunction of A, say psi k. That means psi k satisfies the corresponding eigenvalue equation. A operating on psi k equals eigenvalue ak times psi k. The expectation value for psi k is bracket A equals to the integral over all space of psi k star times A operating on psi k dx. Now A operating on psi k equals ak times psi k. We can pull ak out of the integral. We get ak times the integral over all space of psi k star psi k dx. Now psi k is a normalized wave function, so this integral gives 1, and we finally obtain just ak. So, for an eigenfunction psi k of an operator A, the expectation value is just the corresponding eigenvalue. Now for case 2. This is more general. Let's take the wave function to be a superposition of eigenfunctions of operator A. That is, psi equals a linear combination, sum over all k, of bk times psi k, where bk are the expansion coefficients, potentially complex, and psi k are the eigenfunctions of operator A. The expectation value for this more general wave function is bracket A equals to the integral over all space of psi star A hat psi dx. That becomes inserting the sum, the integral over, now we insert the psi star, which is the sum over all k of bk psi k parentheses star times A operating on sum over q bq psi q dx. Now A can be pulled into the sum and past the expansion coefficient to operate directly on psi q. And since psi q is an eigenfunction of A, we will obtain the corresponding eigenvalue. Also, we can pull out the two sums outside of the integral. We get a double sum, sum over k, sum over q of bk star bq times aq as a result from operating A on psi q times the integral of minus infinity to plus infinity of psi k star psi q dx. This integral is 0 unless k equal q, and therefore the double sum simplifies to a single sum. We get the sum over q of bk star bq star bq times AQ, or in other words, the sum over Q of the norm of BQ squared times AQ. We see that the expectation value for a general superposition wave function is a weighted average of eigenvalues, while the norm squares of the expansion coefficients are the weighing factors. In conclusion, quantum theory is a statistical theory that can give us information only about the average result. It cannot predict the outcomes of individual measurements.